Hi, my name is Lorraine Goeuriot. Before I start, I would like to thank the organizers for inviting me to give a presentation at the workshop, and also really apologize for not being able to present it live. Okay, so the title of my talk is Exploiting Clinical Data to Build Patient Trajectories. So this is the outline of the talk. I will start with presenting the kind of medical data that we're working with. And then I will define what is a patient trajectory. Based on that, I'll give you the general principles of predictions made on patient trajectories. And then I will present you the application of these principles and this work to 3 different use cases that are, I think, incrementally challenging. And then I will give you a few conclusions. To start with, I will describe you what kind of medical data can be found, especially what kind of textual medical data can be found. So the first category is the patient-specific information. So that's all the information that applies to individual patients and that helps healthcare providers, administrators, and researchers communicate to and about the condition of a patient. Within this category, we distinguish structured information, so that's all the lab results, vital signs that can be recorded during a visit at a doctor or a hospital, and the narrative information, which is all the history and physical progress notes and all the reports that are generated by medical professionals. The second category is called knowledge-based information, and that's all the information that has been derived and organized from observational and experimental research. So you're probably aware of that because that's what you're doing on a regular basis when you publish your research. So we distinguish here primary information. So that's all the original research that's published in books, journals, conferences, and secondary research, which is all the summaries of primary original research published in the same journals, magazines, books, or websites. Now with the web now, I think we can also consider a third category being the user-generated content. But that's a whole new world and territory where anyone can write anything. So that's a bit different and more challenging. Now, in this talk, I'm only going to focus on patient-specific information. So here, we only interested in everything that tells us about a patient's condition. So the first category within patient-specific information was the structured information. So that's all the lab results and vital signs that can be recorded directly into a database. So this is mostly numerical values and codes that can easily be recorded and exploited by algorithms. Now for the second category, it's more of a challenge. So hospitals and medical professionals generate a lot of textual data, such as this one, and it's always unstructured. It's non-anonymized, which makes it more challenging to be used by researchers afterwards. And it's very often noisy. It can contain abbreviations, acronyms, and also a highly specialized vocabulary, as you can see in the example here. So the example here is a discharge summary. So that's a document given to the patient when they get out of the hospital. And it's extracted from an open access data set called MIMIC. Now, based on the data that we've just seen, what is a trajectory? What is a patient trajectory? So a health trajectory can be defined as the dynamic, so changing, course of the health and illness of a patient. Now, this course is changing over time. It's also across different services, hospitals, and should contain all possible records. Now, imagine that would mean that from your birth, there's some form of record of every single visit and every single exam you've done for your health. Now, realistically speaking, I don't think there's anywhere or anyone that has such such a database of all these information. But within one single service, for instance, there can be pretty comprehensive trajectories for all the patients that are followed by the same service, the same doctors, the same clinic, and all these things. So quite often we're focusing on a narrower set, a narrower trajectory. Now, what does it mean to predict something out of a patient trajectory? So if you have a set of records over time for a given patient, the purpose of the prediction is to be able to guess what will happen at time n+1, given the previous n visits. So given a patient, the recording of her or his previous n visits in a given service over time, we would like to predict what happens at the n+1 visit. So either the diagnosis or the outcome of the visit. Now, technically speaking, how do we conduct such prediction? So first we start with the data, the original data that has to be labeled. So that's a first challenge. We need some exploitable data that is labeled so that we can train the algorithms. Based on this data now, we need to define an input representation. So we need to transform this data into vectors or a representation that can be understood and used by a machine learning algorithm. Then we need to be able to train this algorithm so that it gives quality prediction and useful prediction for the medical professionals. And also one last challenge that I'm actually not going to address at all in this talk, but still is of very high interest, which is the explainability of the prediction. So that's, I think, one of the ground elements of the collaboration between AI and the medical field is to be able to explain what we're doing and why the algorithms are predicting this or that. Now, based on these very general principles, I'm going to present you 3 use cases I've been working on recently. So the first one is a collaboration with a service in the hospital in Grenoble that deals with sleep apnea patients. So the identification of obstructive sleep apnea, also called OSA, relies on a laborious and expensive exam called polysomnography. So this exam actually consists in measuring all sorts of things on a given patient that would go to the hospital and spend the night there. The machine will record a lot of different signals from the patient, and based on all these signals, as you can see on the bottom left of my slide, then an expert will determine whether this patient suffers from obstructive sleep apnea or not. Now, actually, the that in the literature, we can see that other factors that are much easier to measure can be also good indicators of sleep apnea, and that using machine learning methods can help predicting which factors would be more revealing, and also predicting if the patient has sleep apnea or not. So we worked with 1,000 patients from the university hospital. These patients are using a device to sleep. So that's some form of a mask that they use every single night. So they regularly monitored and they regularly visit the service we're working with. So there's a database recording their state with more than 20 features, recording their age, gender, whether they smoke, drink alcohol, exercise, their weight, their blood pressure, and all these things. And the purpose of the paper was to design a methodology to systematically investigate how we could select the most discriminant attributes, and also which algorithm would be the most efficient for a use case, and finally how we can validate that. So there are 3 different parts in this study. And so the first one, the data preparation part, here to do so, we had first, of course, as with any such study, we had to clean the data set by removing inconsistencies, outliers, missing values. We also had to do some oversampling to get a balanced data set. And finally, we used naive-based methods on the data to get which attributes were the most discriminant in the data set. Now, the second part with the algorithm selection, so based on this balanced, clean data set and the set of the most discriminant attributes, we run over 60 algorithms to be able to tell which ones were the most efficient for our use case and our data. And finally, we validate the methods with the selected algorithm with several rounds of cross-validation and random sampling. So without going into all the details, because I won't have enough time, and you can check them in the paper if you're interested, because it has been published in CIKM. So the first part, the most discriminant attributes. So based on experimental evidence, we showed that the age, smoking, body mass index were among all were very discriminant attributes. This is actually comparable to state-of-the-art results, and these results are, for instance, very interesting for our medical colleagues that showed great interest into the correlation between sleep apnea and all the other factors. Now, for the algorithm selection, we tested regression algorithms to calculate an apnea hypopnea index, which is the measure that can predict, that can tell whether a patient has sleep apnea or not. And we tested also classification algorithms to classify patients among normal, mild, moderate, or severe sleep apnea. So we tested 60 different algorithms with a split validation and multiple iterations, and showed that gradient boosting and extra trees were the best regressors for our problem, and that random forest and extra trees were the best classifiers. Now, the results that we obtain are actually comparable or higher than the state of the art, although none of all these papers are actually experimenting on the same data sets. So it is somehow comparable, but because we're all working with our own set of patients and our own database, they're only just comparable. Okay, so now the second use case that I'm going to present you is a use case actually using state-of-the-art data set. The question was, what if we including now some text into the patient trajectory? In the previous use case, the sleep apnea patient, there is no text. All the data is only numerical values. Here, we wanted to investigate whether we could use text to predict the outcome of a patient trajectory. So we used a mimic data set, which is a set of de-identified clinical data of around 48,000 patients recorded between 2001 and 2012 in a critical care unit in Boston. And for each patient, these data sets contains a set of admissions, each one consisting of several clinical notes and a sequence of diagnoses given in ICD codes. There can be several several diagnoses for a given admission and several clinical notes as well for a given admission. And a patient can have only one admission or several. So that's illustrated in the picture on the right. Now the purpose is, given a patient trajectory with T admissions with their diagnosis codes and the notes, can we predict the outcome of the next admission? So the prediction can either be what will be the most probable diagnosis, or what is the mortality probability, or the probability that the next admission will take place within 30 days. Now, the state-of-the-art shows that the predictions solely based on ICD codes can give good results. Using the text can also help, but it brings some noise. Now, what we wanted to investigate was whether we could use a conceptual representation of the text rather than just a bag of words approach. There's, in the medical domain and in English, there's a lot of knowledge bases that can be used, so we try to use them. So we've conducted this study with a master's student, and we submitted a paper that is under review at the moment. And in this paper, we investigated the transformation of the text into a bag of concepts. So we've tested several threshold methods, several filtering methods to build the bag of concepts. And then we transform these bag of concepts into vectors that would be then given to a neural network that would predict either the diagnosis, the mortality, or the readmission. Okay, so I'm throwing some numbers here, and I have no time to go into the details, but I just want to tell you what we learned from it. So in the first table, you can see the diagnosis prediction performance. And we wanted to investigate what kind of knowledge base we could use. Here you have two knowledge bases. So CUI is concept unique identifiers from UMLS, which is a very broad knowledge base. And the CCS is actually a smaller concept set that is mapped with UMLS CUIs. And so here you have the results across all the metrics of the prediction using either CUIs, CCS, or both. And the results show that actually combining them is the best option, again, on our data. In the following table, I show here the results for 3 different prediction tasks. So diagnosis code prediction, mortality prediction, and 30 days readmission prediction. And here we're using 2 neural networks. So the representation is always the best one, and here it's only bag of concepts. So the first method we're using is feed-forward networks. So feed-forward networks will only use the last, the last visit. So the admission T of the patient. And the second one is gated recurrent units. It's a kind of recurrent neural networks, and it takes into account the whole sequence of visits. And the results here show that actually taking into account the entire set of visits can be very good to predict, for instance, the mortality, but can be pretty bad to predict the 30 days readmission, which is much better predicted with only the last visit. So depending on the use case and what we want to predict, the entire history of the patient can or cannot be useful. And the final table is a comparison with a few state-of-the-art results. Now, it's choosing the most flattering metrics, obviously, but it only shows that actually we can, using only the concepts contained in the text, get a pretty good prediction of the trajectory of a patient. And the final slide here, the final use case, is actually the most challenging and the most recent work. So it's really a work in progress. But here the question is, what if we're working with textual data, and if this data is in French and not in English? So that's even more challenging because we don't have all the knowledge bases and we don't have all the training data. So we're working with a French GP emergency service called SOS Médecins, and they have a database with numerical and textual, pretty noisy data on all their patients. And we've tried to predict reaccess, hospitalization, and diagnosis. You can see them here, based on state-of-the-art methods. And you can see that for the reaccess, for example, we can get some satisfying results, but they're still pretty low for other kinds of prediction. But BERT on its own can actually give us, so Flaubert is a French BERT, can give us actually some pretty good results on their own. Now, as I said, that's a work in progress, so we're still pre-processing, understanding the data, and we're hoping we'll be able to get much better results soon. Now, to conclude my talk, I hope I convinced you that with labeled data, labeled textual data, we can actually do some quality prediction on patient trajectories. Adding semantic features can help the prediction, but the biggest challenge, again, as usual, is the lack of data and the lack of training data, and especially when one works with another language, language other than English, it's the lack of data and knowledge basis. But the good thing is that there's a growing interest of the medical community for artificial intelligence, which is pretty promising because we're getting more data, more collaborations. Thank you very much for your attention. And I'm again very sorry I'm not here to answer your questions, but you can get in touch with me via email or on Twitter. And I hope you'll have a great day and a great workshop today. Thank you.